Hi there, welcome back. Today we are discussing section 3.3, curve sketching. In the second video, we're going to try to tackle this second learning objective, discuss and apply a general procedure for sketching graphs. And here's the basic idea. I want to take this notion of calculus and say, sure, I know how to find derivatives and limits and so forth. I want to use them to figure out the big picture for any given function. So for instance, here's a graph, here's a function f of x that we're trying to look at. It's a polynomial because it's just got x to some power for its terms. And then we want to know all these different things about it. And the goal is that we're supposed to use all these parts a through g to sketch the graph of a function. This is kind of an antiquated notion. This type of problem comes from before graphing utilities were really prevalent. So really, all we had in order to get a picture for some function was calculus, essentially. And that's sort of not true to some extent, because graphing calculators and Wolfram Alpha and other programs will do a lot of the job for us. But there's actually, I would say, two distinct reasons why this is still valuable. If we had some relative maximum, for instance, some bump up in the graph at x equals square root of 2, just from a graph of the function, it would be very hard for me to determine anything beyond, it seems like it's between 1 and 2. I wouldn't have a great idea of exactly what value that occurred at. Well, calculus would allow us, taking the derivative, setting it equal to 0, would allow us to find the exact coordinate at which this happens. So if some degree of precision was necessary, we'd be able to get as much accuracy as possible from using calculus. The other is that if I graph something on a graphing calculator and I'm not totally sure how many times the graph can change direction, for instance, or where its asymptotes might be, then I might graph the function and not actually include all of those interesting values in the picture. So by using calculus to help narrow down those opportunities as well, then I can make sure that I get a picture of all the interesting points on this function. So that's the motivation for this. In general, since we can use calculators in our class, we'll be making use of these things only to augment our understanding of what the picture looks like, because I have no problem at all with you putting this into Wolfram Alpha or graphing it and seeing what it looks like just in a general sense. Okay, so let's dig in though. First thing on the list is domain, which is actually pretty easy for this function because it just looks like x to some power, x to some other power. So finding its domain is fine. There's no division by 0, there's no square roots of negatives, there's no logarithms, so our domain is going to be all real numbers. Intercepts, so if we start with vertical intercept, that's the easy one. Letting x equal 0 and plugging that into every x value in our function, we get an output of 3. So our vertical intercept is 0, 3. Horizontal intercepts are a little more sensitive. In this case, we're supposed to set y equal to 0 and solve. And so we don't even have a quadratic formula that helps us deal with x to the 4th power. But that's actually okay. We can use some sort of either a solve feature on a calculator or Wolfram Alpha to get some pretty decent approximation values there. So in general, I won't be expecting you to do this with x to the 4th. Okay, part C was asymptotes. So if we start with horizontal, I'm in charge of looking at this limit as x goes to infinity. Well, okay, so if I want to know the behavior of all of this stuff, it seems kind of complicated because I've got x's positive here, but then subtracting some other x's, subtracting some other x's, adding 3. But if we recall from some good algebra classes, that basically what this amounts to is x to the 4th. All of this stuff, as x gets really, really large, is going to reduce to this term that pulls the hardest, basically. So 1/2 x to the 4th is basically the one that's going to be in charge for sufficiently large values of x. That makes it a lot easier to think about what happens as x gets large. A very large number to the 4th power is even larger. A half of that doesn't really spoil it, so as x gets bigger and bigger, so will the output of this function. So the values are going to be approaching infinity as we move along the graph to the right. We're also supposed to check x going to negative infinity. The same thing is true here, though. We should only have to look at the first, well, the leading term in the sense that it has the largest exponent on it. And if we, again, compare that term with very large negative numbers for x, raising that to the 4th power actually makes them positive again. We're 4th power, and even power is going to make those numbers positive. So we have infinity again. Now, we're only supposed to care about these limits if they're finite values, if they're 0 or -2 or 10 or something like that. Infinity should imply that there aren't any horizontal asymptotes, because that was the real question. So neither limit is finite, so we don't have any horizontal asymptotes for this function. The other half of this, for finding vertical asymptotes, our most tempting policy is basically to look for domain errors, places where we would divide by 0, places where we would take the square root of a negative number to get a non-real answer like that. But that's not going to happen in this case. We've got x to the fourth, x to the third, and so there aren't any chances to look for domain errors in this case. And this is kind of a naive conclusion. This is definitely more complicated, but our conclusion in that event is that we're not going to find any vertical asymptotes for this function. Okay, so then we're supposed to move on to relative extrema. Well, relative extrema, increasing, decreasing, this all depends on the derivative of the function. So that should be our first step. So f prime is, well, derivative of all this, and that's actually just power rule, which we're pretty good at. So the 4 comes down to give us 2x to the third, and then so on down the line, and the constant is gone. So we're supposed to take this and solve f prime equals 0, and so there's our expressions that equal to 0. If you note, there's a factor of 2x in each of those terms that we could pull out. So then the leftover stuff looks like x squared minus x minus 2. And then this inside part, this quadratic in the middle, can actually factor a little bit further, can turn into a product of these linear terms. So we've got three solutions: x equals 0, x equals 2, x equals -1. And reusing this analogy of the job interview, basically these are our three candidates. These are the three people, 0, 2, and -1, who are going to interview for the positions of relative maximum, relative minimum. But it's actually possible to come there and get no job at all. You could be neither a max nor a min. But we won't know that till we test. There's several valid methods here, one of which, for my class anyway, is just using the graph of the function. But the formal methods are first derivative test and second derivative test. In this case, I picked the second derivative test just because it's actually not all that hard to find the second derivative for this particular function. There's no product rule or quotient rule or crazy stuff going on, so f double prime is actually pretty easy to figure out. So with another application of power rule, we got 6x squared minus 4x and minus 4 for f double prime. So then we're supposed to take our critical values, let's start with 0, and plug that into our second derivative function here. So if we plug in x equals 0, what we get is an output of -4, and that means, just recall that the rationale for this is that if we have a negative second derivative, that means the graph is curved downward. And since we have a critical point there, that must mean that this is a maximum value at that point, because the graph is curved down, but the derivative goes to 0 for a split second. We can find the actual output by going all the way back to our f function, plugging in 0. And actually, remember, we already did this because we figured that 0 was also the y, 0, 3 was also the y-intercept, the vertical intercept. So this point has more than one interesting thing going on for it. So we continue testing points. So we've got -1 for our second derivative, and this, I can make the slides, but apologize for that. It's correct on the other page, but for some reason I changed my mind. So at plugging in -1, we get an output of 6. So that implies, these must have been swapped, so I'm sorry about that. So we've got positive curvature. So that means that our graph is curves upward at that point. And that's going to imply, by the second derivative test, that our x value at -1 is going to be the location of a relative minimum. And then plugging in to get the actual point, we go back to the original function. So it's always sort of interesting, this interplay between using the derivative, the second derivative, and the original function back again. But since this is actually looking for a point on the graph, we should be going all the way back to f, not its rates of change, in order to find the height on the graph. So this is just a written reminder of that. It's not saying, because we got 6 here, that's saying something about the curvature of the graph. This is not actually the output of f, it's the output of f double prime. So this is telling me that the graph is curved upward there, not that it's at a height of 6. Okay, so the last one to try out, we've got x equals 2, and so we'd have a relative minimum at this spot because all of our curvatures are, our curvature at this point is positive. So since the graph is curved up, we'd be seeing a relative minimum at that value. Once more, plugging that into our original function, if we take 2 and go back to the original 1/2 x to the 4th, that whole deal, we should get something like -7/3. Okay, almost there. Intervals of increase and decrease, we're really already on track with this because we know the places where it could possibly change direction. This is what calculus has done for us. Because these were the solutions for critical points, we know that at x equals -2, 0, and 1, these are the only places where the graph can change direction. So they're also the places we should test between in order to determine what direction they're actually going. So this is where the visual thing we use this little diagram with the number line, and then use f prime being positive or negative to judge increasing and decreasing. Keep in mind that I personally don't really have a problem with using the graph at this point to determine increasing and decreasing, since we know the exact values where these things can change its mind. Okay, so test points. We have 1, 2, 3, 4 regions to work with. So we can pick anything, but I'll pick -2 just because it's in this leftmost region. It's definitely less than -1, but you could have picked anything over here. So all I really care about is this part, the fact that it's a negative number. So that means that f is decreasing in that region. So -0.5 would put us right here in the second region. So if we plug in -0.5, again, this is where calculator's handy. Most important feature there is that the output is positive. So that must mean the function is increasing during that interval. We'll test at x equals 1 here. So at x equals 1, f prime is -4. So negative derivative means the graph is headed downward. And then finally, one last point, I checked x equals 3. I'm picking whole numbers just because they're slightly easier to compute. Here I didn't have a choice because there aren't any whole numbers between -1 and 0, but pick the next best thing, -1/2. Okay, so plug in plug in 3 to the f prime function, get another positive slope, so the function's increasing over that period. Okay, so concave up, concave down, and then finally inflection points. These are all things that rely on the second derivative. Now, we might as well make use of the work we did before and grab f double prime and say, hey, okay, we already computed this, so let's make use of it. And then from there, it works just like finding relative extrema, intervals of increase and decrease. We should basically take this second derivative and set it equal to 0. These are the most tempting opportunities for when the graph can change curvature. So keep in mind, at any of these steps, we should also be checking where these derivatives are equal to 0 and where they could be undefined. But neither the first derivative of this function, neither f prime, nor this thing, 6x squared minus 4x minus 4, would be undefined for any values of x. They're not. There's no division by 0, no square roots of negatives, and so on. Okay, so quadratic formula can help us out with this. So factoring, I think, is off the table unless you're really good with your radicals. So for there's the exact value, 1 plus or minus square root of 7 all over 3. Those are the two inputs, but the approximate values, just for the sake of graphing, are close to -1/2 and a little bit above 1. So these are the only two places where the graph could change its curvature. So we'll do a test just like we did for increasing and decreasing and test between these values. Okay, so we have 1, 2, 3 regions. The one on the far left, I'm testing -1. And notice that we're going to the second derivative because we're asking about curvature, how this graph is curved at this point. So we get a value of 6, and that implies that the graph is curved upward for that region. If we test here in the middle, we can try out x equals 0. And then for that particular value, we've got -4, so the graph is curved down at that point. And then finally, one thing on the far right side, we can test x equals 2. That gives us a positive curvature again. So the graph is, it changed its direction in that case. So it's curved up, curved down, and then curved up again. The last thing, we really don't have to do any new computations to find inflection points. We already determined, and bring the picture back here for a sec, we already determined that it changed direction. Here it's curved up, and then it flips over curvature at -0.549. And then it was curved down, and then it became curved up. So right at 1.215, it also changed curvature. That's exactly what it means to be a point of inflection. So each point at which it changed concavity, so in particular, negative 0.5 and 1.21, those are the inputs for our points of inflection. The only other detail, again, is going back to the original function and plugging in these weird inputs for x. So this really is all the way back to that x to the fourth plus x cubed, etc., that original thing, to find the height on the graph. So these are the outputs of those 2 points. And then this is the point at which, without any technology, we'd be able to finally put together some kind of picture. Of course, we could have had the graph along with us this whole way and help give us a visual to inform our work. So this is what it would look like without any kind of adornment. We'd have some kind of indication that these values were around -1 and around 2, some interesting kind of bump up and bump down things would be occurring. But without the calculus, we wouldn't know exactly what those numbers are. Okay, so just in the order in which we found them, here's some notes. So we found a vertical intercept at 0, 3. Horizontal intercepts, we have those values. Then we found relative extrema, maxes and mins. Then we found the 2 points of inflection. And so what we could say is, for instance, here the graph was curved up until that point of inflection, at which point it flips over to curved down. And then it flips over to curved up again over here. Relative max and relative mins, then we've got a high point in its little area, a low point, so it was decreasing until we arrived at -1. Then it's increasing until we arrive at 0. Then it's decreasing again until we get it to an x value of 2. And then it's increasing from that point forward. So there's our general graphing strategy. But again, I do intend that we can have a basic picture of this function modeled to begin with, and then we can only have to modify with the exact values using calculus. That's it for section 3.3. We'll be back with 3.4 in another video.